All right, everybody, welcome back. So, as we were saying before, at the end of the first part of the talk about polar integration, we talked about polar boxes. Now, let's talk about polar non-boxes. Now, I think generally there could be more possible polar non-boxes than just the ones that we're going to see here, but, we can't get it all in. So, for our purposes in this textbook and for the problems that you'll see on WebAssign, the polar non-boxes that we're going to see are going to be regions of this form here, D. They're going to be the set of all points in the plane r comma theta in polar coordinates, where theta is still bounded by two constants, alpha and beta. But now the radii r are bounded between two functions of theta. So let's maybe get like a picture of this. So r equals f1 of theta and r equals f2 of theta are going to be curves in the plane, and they might have some kind of polar nature to them. It's probably likely that they will, since we're talking about polar coordinates here, so we like kind of curves that are nice in polar coordinates. So here's kind of the generic picture that we might see. So along here we have theta equals alpha. Notice that gives us this line here. And the upper bound for theta here is beta. Notice the difference between the two sides of this picture. It looks like here at theta equals to, say, beta, we have f1 of beta is less far out from the origin than f2 of beta is. However, f1 of alpha and f2 of alpha look like they are actually the same distance out from the origin. So the two curves actually intersect there. So sometimes it's going to be necessary to actually solve that equation. Maybe you won't be given that bound alpha. You might have to solve for it or something. So that's fine. That's some extra work, but we'll cross that bridge when we come to it. So then again, it might also not be the case that you have to do that. You might have a polar region that looks like has these nice kind of like lines chopped off on either side. So let's start with the first example here. We'll find the area that is outside of the circle r equals 2, but inside of the circle r equals to 4 cosine of theta. Wait. I thought that circles in polar coordinates had this form r equals constant. What is this circle r equals to 4 cosine of theta? Well, I think we saw that circles centered at the origin have the form r equals constant in polar coordinates. But this circle, r equals to 4 cosine theta, is a circle that is not centered at the origin. Well, then where is it centered? Well, you can do this work yourself, maybe in the comfort of your own home, since you're not leaving there. We can show that r equals to 4 cosine theta is the same thing as the circle of radius 2 centered at the point 2, 0 in the xy plane. So it's circle of radius 2 shifted over to the right by 2. So how do you show this? Well, I don't know. I think I might start by multiplying both sides by r. So that on one side I have r squared, and on the other side I have 4 times r cosine theta. Then you might be able to use some of the identities relating polar coordinates to rectangular ones to change that equation into something rectangular. And then you might have to do a little bit of further manipulation, like, I don't know, maybe complete the square to show that what you get is, in fact, the circle of the form x minus 2 squared plus y squared equals 4. Okay, I've now said way more about that than I wanted to. So let's just draw here as a picture of both of these. We have the circle r equals 2. That one is there. Let's pretend that this is the point 2, 0, right? And here, this other circle is the one that we were just talking about, r equals to 4 cosine of theta. And the region in question that they're asking about is the area that is outside r equals 2, but inside r equals 4 cosine theta. So it's this shaded area here. Looking very nice. So how do we compute the area using a, say, double integral? right? Well, I think the function that we're supposed to integrate is the constant function 1 over this region. That will give us a solid in space that has base this region of the xy plane and has height constant equal to 1. So the volume of that solid is really the same as just the area of its base, right? So then here it says, notice that in this picture, the lower bound for the radii are 2, right? This circle, r equals to 2, gives us the lower bound for the radii. As theta varies from, say, this theta to that one, r goes from 2 out to 4 cosine of theta. Does that make sense? I think the best way to think about modeling your integrals in polar coordinates is to think that way, to think once you've decided what your theta bounds are going to be, look for your r bounds and move radially outward from the origin and say, well, what's the lower r bound then? What's the first thing I hit? That's this one, r equals 2. And then what's the top part you hit? It's this guy, r equals to 4 cosine of theta. Okay. So we can actually save ourselves a little bit of work here because we know that this line, the x-axis, is just theta equals to 0. And we can see that there's some symmetry here. So we really just need to find the area of this top portion and then double it. So we do have to do a little bit of work, though, to find the theta value for this point of intersection. So let's see that. In this top half here, we have that this intersection occurs when 4 cosine of theta equals to 2, right? The two radii are going to be the same. That means that cosine of theta is a half, which, if I remember anything, means that theta is pi over 2/3, right? So, all right. So theta equals pi over 3. I think we could probably say that this one down here is theta equals negative pi over 3. But we won't need that. We'll just find the area as theta goes from, say, 0 to pi over 3, and just double that afterwards. So let's see. As we were saying, we'll integrate the function 1, although, we need to be careful, though. We're going to use polar coordinates. So let's take a look here. We put this 2 out front because we were going to take the thing in half and then double the area that we got at the end. So we'll let theta go from 0 to pi over 3. And our radii, we said, go from 2 to 4 cosine theta. And the function we want to integrate is the constant function 1. But because we are using polar coordinates, we need to multiply again by that Jacobian determinant, r, right? All right, so then we'll do the r integral first, and then the theta integral second, and then double everything after the fact. So let's see what we get. We have 2 times the integral from 0 to pi over 3 of, let's see, well, the integral of r is going to be 1/2 r squared. Then we're going to evaluate that guy at 4 cosine theta and at 2 and take the difference. Notice here that the 2 out front and the 1/2 here can just combine together and cancel each other out. So we'll actually get rid of the 2 right off the bat. We won't need that now. So let's see. 4 cosine of theta all squared gives me 16 cosine squared theta. And 2 squared gives me 4. So we have the difference of these two. So let's see, what do we got now? I can break this integral into 2 pieces. Perhaps that might make my life easier. So we have the integral from 0 to pi over 3 of 16 cosine squared theta minus the integral from 0 to pi over 3 of just 4. Both integrals with respect to theta. And for this first one here, you might recall from Calculus 2 that you can attack it using the half angle identity for cosine, which is that cosine squared of theta equals to 1 plus cosine of 2 theta, all divided by 2. That'll at least turn the 16 into, I think, an 8. And then we'll have 8 plus 8 cosine of 2 theta for that first one. So let's see. Right? Yep. So we'll have the integral from 0 to pi over 3 of 8 plus 8 cosine of 2 theta minus still this integral from 0 to pi over 3 of just the constant value 4. So let's see what we get. We get 8 theta plus, we have 8 times sine of 2 theta, but then we divide by 2, right, by the sort of backwards chain rule. So we end up with 4 sine of 2 theta. We'll evaluate this guy at 0 and pi over 3 and take the difference. And then we also have the integral of 4, which is 4 theta. We'll do the same there, evaluate it at 0 and pi over 3 and take the difference. So we have what? 8 pi over 3 plus, let's see, what is sine of 2 pi over 3? Ooh, I think that's the square root of 3 over 2. So we get 4 times the square root of 3 over 2. And then we subtract 4 pi over 3. Ooh! So 8 pi over 3 and 4 pi over 3, they combine together, or they subtract together to get us just 4 pi over 3. And then 4 times the square root of 3 divided by 2 just gives us 2 times the square root of 3. All right, so that's that area there. That's a pretty standard kind of problem for this section of the textbook. So, watch out for ones like that on, say, WebAssign. Okay, the next example is a little bit more subtle, I want to say. And so there's something going on here that's going to have us really think a little bit more than we did on the last one. So it says, let's find the area inside the cardioid, r equals to 1 plus cosine of theta, and outside the circle, r equals to 3 cosine of theta. Okay, well, you can probably guess that this circle is similar to the odd circle from the last example. It's one that's been shifted over on the x-axis. I think this one will be a shift by 3/2 on the x-axis. That's fine. But this, I don't know if y'all remember what is a cardioid now. So it's this weird kind of heart-looking shape, I guess is where it gets its name, is cardioid. Let's take a look. So, all right, so this circle has center 3/2, 0, and radius also 3/2. And you can do the same kind of trick you did on the bonus homework in the last example to show that. That's fine. But what is this cardioid thing? It looks like this. Okay, it has this very heart-looking shape. Actually, I don't know. It's actually not a very well-drawn heart, if you ask me. But we'll take it. Anyway, this is what this looks like. So let's put the circle, I think, over this, now that we know what this cardioid is. Let's put the circle on top of it. And so now the two curves together look like this. And okay, wait. Let's go back. I have to go back. What was they talking about exactly? They said, let's find the area inside of this cardioid, but outside of this circle. So, okay, now that I see that, I believe that is these two regions here. So this is inside the cardioid, but outside the blue circle. And this is also inside the cardioid, but outside the blue circle. So again, we get this nice kind of symmetry, right? I like this symmetry. Okay, so we can really just restrict to this one shaded region here and just compute that one's area and double it, right? Just like we did in the last example. So we just had to find this. But there's something very strange going on with this one. When we go to find our r bounds, we might be having to break this integral into two pieces. And so notice, I guess this is the big warning here. This shaded region has two pieces. One that's on the right side of the y-axis, and the other that's on the left side of the y-axis. And notice that what's different there. So on the left side of the y-axis, for this half of the shaded region, it looks like the lower radius bound, the lower r bound, is this circle, r equals to 3 cosine of theta. And the upper radius bound is the cardioid, 1 plus cosine of theta. So the lower bound and the upper bound are both functions of theta. However, what happens when we cross over the y-axis here? On the other side, it looks like the upper bound for r is still the cardioid, 1 plus cosine theta, but the lower bound now is 0. Notice here on the y-axis, along this line, if you move radially outward from the origin, you start at 0 there and move all the way up to the cardioid. Whereas just, a little bit over theta-wise, you didn't start at 0, you started here along this circle, 3 cosine theta. So there's going to have to be two different integrals here. And what is the angle that gives us this y-axis? I believe that is the angle, the angle is theta equals pi over 2, right? So before pi over 2 and after pi over 2, we're going to have different r bounds. The lower bounds of integration for r are going to be different for those two pieces. Okay, so let's watch it go. So, oh, right. So first we have to find also this point of intersection, right, between the two curves, because that'll be where we start theta-wise. So that happens when the two radii are equal, and so the restriction there is also, we're going to look in the first quadrant, so that happens between theta equals 0 and theta equals pi over 2. So let's solve this guy. Let's see. We get 1 equals 2 cosine of theta, so cosine of theta is a half. Oh, okay, so again, we have theta is pi over 3. Looks good. So then the right side of that region, let's go back again and just look at the picture again, is that here theta is pi over 3 here, and theta is pi over 2 at the y-axis. So this first region of integration has lower theta bound pi over 3 and upper theta bound pi over 2. And as we discussed before, its r bounds are 3 cosine theta and 1 plus cosine theta. Oh, but that's not the integral that I put here first. Oh, wait, yeah, it is. Yeah, it is. Oh, wait, yeah, it is. Okay, sorry. Misspeaking. Going crazy here. Anyway, so theta goes from pi over 3 to pi over 2, and r goes from 3 cosine theta to 1 plus cosine theta. And again, we're trying to find area, so we're going to integrate the constant function 1. But because we're pulling back to polar coordinates, we need to multiply by r, right? That Jacobian determinant for polar coordinates. So, okay, here we go. So what's the integral of r with respect to r? It's 1/2 r squared, right? So we'll have 1/2 times 1 plus cosine theta squared minus 1/2 times 3 cosine theta all squared. Okay, so that's 9 cosine squared theta, okay. And I guess if we do some of the simplification here, it looks like I skipped a step, but that's fine. You can just do this in the comfort of your own home now, which should be a very comfortable place for you by this point. So it turns out that the integrand becomes 1/2 plus cosine of theta minus 4 cosine squared of theta. And we will integrate this one as theta goes from pi over 3 to pi over 2. Okay, it looks like we're going to have to use the half angle identity for cosine again. It seems like those are rather ubiquitous with regards to this polar coordinate nonsense. So if you forgot what those were, you probably will remember them by the end of the time you do your homework. Anyway, we invoke that one and we turn what was 4 cosine squared theta into 4 times 1 plus cosine of 2 theta, all divided by 2. Okay, and so then we can simplify that further, and our whole expression that we want to integrate becomes 1/2 plus cosine of theta minus 2 cosine of 2 theta. Okay. And it looks like then we can simplify even further into 1/2 minus 2 becomes negative 3/2. Okay, now I think we can finally do this integral. So we get minus 3/2 theta plus sine of theta minus sine of 2 theta. Notice that we would have had 2 sine of 2 theta, but then we have to divide by 2 again because of the sort of backwards chain rule. Okay, and we will evaluate this, guys, at theta equals to pi over 2 and theta equals to pi over 3 and take the difference. So let's see, at pi over 2, we get minus 3 pi over 4 plus sine of pi over 2, which is 1, minus sine of pi, which is 0. And then we subtract, oh, sorry, this should be a minus sign here. Luckily, that number is 0, so it's irrelevant, but that's a small mistake there. Okay, and then moving on, we will subtract now this expression evaluated at theta equals to pi over 3. Well, let's see what we get. We'll get minus pi over 2 plus sine of pi over 3, which is the square root of 3 over 2, minus sine of 2 pi over 3, which is also the square root of 3 over 2. So the square root of 3 over 2's cancel, and we're left with minus 3 pi over 4 plus 1 plus pi over 2. So that gives us minus pi over 4 plus 1. Now remember, that was only the the right half of that region that we were trying to find the area of. So now we have to do the other side. whose lower r bound is now 0, as we discussed before. And, oh yeah, we kind of rushed this part under the rug. Theta starts at pi over 2 there and ends at pi. Maybe we can go back. Let's go back and take a look at that. Here's that picture again. So here, this region is the one whose area we want to find now. So theta starts at pi over 2 and ends at pi here. You can solve that cardioid goes back to 0. 1 plus cosine of theta equals to 0 when cosine of theta is minus 1, which means theta is pi. Okay. So there's a little bit of work we're brushing under the rug there, but that's fine. I think you can handle it. Okay, so the same idea again. We're integrating the constant function 1 over that region, but we have to still multiply it by r because of the fact that we're using polar coordinates, right? So we get, again, 1/2 r squared in the first round, and we just have to square 1 plus cosine theta, since 0 squared is 0. So we get 1 plus 2 cosine theta plus cosine squared theta. And, oh my gosh, this half angle identity is here again. And notice here we also are multiplying everything by a half because we have 1/2 r squared for our integral. So I'm just going to multiply everything through by half and invoke the half angle identity as well. So we get 1/2 plus cosine of theta plus 1/2 times 1 plus cosine of 2 theta all over 2. Okay, so that becomes 1/4 times 1 plus cosine of 2 theta. And you can combine the 1/4 there with 1/2 there and get 3/4 as your constant for your integrand. So we'll have 3/4 plus cosine of theta plus 1/4 cosine of 2 theta that we will integrate from pi over 2 to pi with respect to theta. Well, what we get is 3/4 theta plus sine of theta plus 1/8 sine of 2 theta. And we'll evaluate this guy at theta equals to pi and theta equals to pi over 2 and take the difference. So at pi, we get 3 pi over 4 plus sine of pi, which is 0, plus 1/8 sine of 2 pi, which is also 0, minus the quantity evaluated at pi over 2, which gives us what? 3 pi over 8, plus sine of pi over 2, which is 1, plus 1/8 sine of pi, which is 0. And so we can put these guys together, and we get 3 pi over 4 minus 3 pi over 8. That becomes just 3 pi over 8. And then we also have here minus 1. Okay, so that's the second side of that region of integration. So now let's add these two together. What do we get? We had, for the first piece, we had minus pi over 4 plus 1. And for the second piece, we had 3 pi over 8 minus 1. So the 1 and minus 1 cancel, and we're left with just pi over 8. But then remember, we only ultimately found the area of half of that region because there was the bottom portion too that we decided to just neglect because we could get it by symmetry at the end, which we'll do right now. So we'll double what we have here, and we get the total area in question there is pi over 4. So this example is pretty weird, and I think it's probably about the weirdest kind of example that you'll see in this context of polar integration, where you really have to mind what your bounds are for r. And it could be one of these instances where you end up having to break your integral into actually 2 pieces because the r bounds are different in the 2 different pieces. So be on the lookout for that as you go about and do your homework. But I think that they couldn't get too much weirder than this one. So be vigilant and come back next time. I think we can probably still get more talk into this first lecture where we'll take these polar coordinates and bring them into 3D and start doing some triple integrals where we get to keep polar coordinates on one of the sort of coordinate planes and then keep the third coordinate in space to be itself. So tune in next time for that talk about what's called cylindrical coordinates.